Hi, welcome back to 345 Delta Foxtrot. Okay, this video is Rivets Part 5, experiment number 2, and it's using thin metal. The last video was Part 4, experiment number 1, optimizing the shop head, and that was using thick metal. So this experiment is very similar to the previous one, except for the thickness of the metal. I'm not going to go over anything that I've already talked about. If you're just now tuning in, I recommend that you go back and watch the last two videos. Watch Rivets Part 3 and Part 4. Otherwise, you're going to have trouble following what's going on. Okay, the rivets for this experiment were all 426 AD 3-3s. They're flathead rivets. Because they're flathead, both layers of metal were dimpled, and H was just under 1.5D. It was very close to 1.5D. Okay, the aluminum for this experiment was all the normal Vans skin aluminum, at least for an RV10. I'm not positive about all the other RVs. It's the 2024 T3 alloy. It's about 16 thousandths thick. I just measured a few samples and I got between 16 and 17 and a half thousandths, I think. And as I already mentioned, both layers of metal were dimpled. Okay, here's the experiment. It's very similar to experiment number 1. You start off with the squeezer not squeezing the rivet at all, just barely not squeezing at all, and that would be 0 turns. And in the last experiment, I was able to change the squeezer gap by 2 turns, where each turn is a 32nd of an inch, and the rivet did not fall out. However, in this experiment, the rivet did fall out. So I had to go to at least 2.5 turns before there was anything to measure. And then everything else in terms of the squeezer setting is the same as it was in experiment number 1. Then I measured the width of measured W, which is the width of the shop head, in inches, and that's in the next column. And because the metal was dimpled, it's very difficult or close to impossible to measure the thickness of the shop head. So that's unknown. And then if you convert the width of the shop head to something times D, that's the next column. And you might notice that sample number 4 is 1.48 times D, which is almost exactly the nominal value, or the size of the hole in the Cleveland Aircraft Tools rivet gauge, which is 1.5 times D. So sample number 4 is what I would call the nominal sample. Then the next to last column is the strength at which they failed in pounds. And the values are significantly lower than they were in experiment number 1. We'll talk about just how much in the next slide. And then the last column is the failure mode, how the samples actually failed. And it's also very similar to experiment number 1. The first 3 samples, the shop head failed, and the last 3 samples, in tension, the factory head failed. And the last sample, the last row at the bottom, that's measuring with shear stress, and it's nominally squeezed. And in shear, the failure is significantly higher than it is in tension. It did go down compared to the thick metal, but the nominally squeezed samples in tension were somewhere around 120 pounds, but in shear, it's up around 250 pounds. Okay, this is comparing the thin metal to the thick metal. The thick metal is in green and the thin metal is in orange. And the first two columns in green and orange are the width of the, or diameter of the shop head. And you'll see that for a given squeezer setting, I'm getting essentially the same values. So, for example, sample number 4 for the thick metal was 1.49 times D, and for the thin metal it was 1.48 times D. So it's comparable in both experiments. And then the next two columns are the strength that I measured. And you'll see that the thin metal is significantly lower values than the thick metal. And if you look at the far column on the right, that's the strength of the thin metal divided by the strength of the thick metal. So for what we'll call properly squeezed, that's the last three samples, 4, 5, and 6, the ratio is right around 0.42. So the thin metal samples are failing at a third to a half of the thick metal. Now, for shear strength, down at the bottom row, it's a little bit better. There, the thin metal is only about 75% of the thick metal. Then the failure modes were essentially the same in both cases. The shop head for the first three samples and the factory head for the last three, 4, 5, and 6. Now, one thing I want to mention and make clear is that in experiment number 1, we were measuring the strength of the rivet. We were using nice thick metal, nice strong metal, and it's the rivet that was failing. In this experiment, what we're seeing is the metal fail. The thin metal is failing. The rivet is significantly stronger than the metal, and the rivet is just enlarging the hole and pulling through the hole in the metal. Okay, this is a picture of all the samples after they failed. And the first one on the left side is measuring the shear strength. And then going from left to right, the next samples are 2, 3, 4, 5, and 6 for tensile strength. And the top row is the factory head, and the bottom row is the shop head. And you can see on samples 2 and 3, the shop head just wasn't squeezed enough, and it pulled right through the hole. And then on samples 4, 5, and 6, it's totally different. There, the shop head is stronger than the factory head, and it's the factory head that pulled through the hole. Okay, so what did we learn from this experiment, or these two experiments? The first thing that I learned is that you want to squeeze a little bit more than I was squeezing before. You want to squeeze so that the shop head is somewhere around 1.4 to 1.8 times D. As I mentioned, the hole in the Cleveland Aircraft Tools rivet gauge is 1.5 times D. And before, I was allowing rivets, you know, anywhere close, I thought was okay. Now I'm squeezing rivets so that the shop head is always bigger than 1.5 times D. And point number 2 is it's hard to over squeeze the rivets, and that's one of the reasons I've changed. Is I don't see any downside to going to squeezing harder and making sure that none of the shop heads will fit through the hole in the rivet gauge. And point number 3 is we're still getting pretty consistent results. I thought that with the thin metal, the results might be fairly inconsistent, but we're still getting fairly consistent values. And point number 4 is the rivets are stronger than the metal for the thin metal. The thin metal is about 43% as strong as the rivets, which is the thick metal. And there's a table at the bottom here showing basically how things came out. In tension for the thick metal and properly riveted, it's about 280 pounds, and for the thin metal, it's about 120 pounds. And in shear, it's about 330 pounds for the thick metal and about 250 pounds for the thin metal. Point number 5 is particularly for the thin metal, the shear strength is significantly better than the tensile strength. In fact, for the thin metal, the shear strength is more than 2x. It's 250 pounds versus 120 pounds for shear versus tension. So the shear strength did get, lower for the thin metal, but not nearly as much as it did for the tensile strength. Okay, this raises some interesting questions. There's a kind of a saying that the more you know that you don't know, and that's kind of the case here. As we've learned a little bit more about the strength of rivets, we've learned some more questions to ask about the strength of rivets. The first one is, why does Vans use thin aluminum? And I suspect that it's largely historical. We'll never really know the answer to this unless Vans chimes in, unfortunately. But I suspect that they started using thin aluminum back in the 1970s, and they've just continued since then. It's also possible that the alloy that they use, the 2024-T3 alloy, is, and with the pure aluminum cladding, is only available in a limited number of thicknesses. And so there just might not be all that many choices. I don't know. The second question is, why does Vans use number 3 rivets? Why not just use number 4 rivets? They're clearly stronger. What's the point of using number 3 rivets? And again, I suspect that that's largely historical. Number 4 rivets, since they're bigger in diameter, are a little bit harder to squeeze or harder to rivet than a number 3 rivet. And back in the old days, I don't think they had tungsten bucking bars. Now that tungsten bucking bars are easily available, I suspect that if you were redesigning the RV10, it might make sense to use number 4 rivets everywhere. That, you know, just take the free extra strength, even if you don't really need it. You'd end up with a stronger airframe. And then question number 3 is, why does Vans use solid rivets? Why not just use pop rivets or pulled rivets or blind rivets or whatever you want to call them? And we can look at that question in a little bit more detail. In section 5.4 of the plans, Vans talks about using Cherry Max rivets. And Cherry Max rivets are the strongest pulled rivet available. And my understanding is that you can use a Cherry Max rivet anywhere that you have a solid rivet. The Cherry Max rivets are actually stronger than a solid rivet. And so you look at the Aircraft Spruce website, and I looked at the CR 3212-4-2 Cherry Max rivet. The CR3 means that it's Cherry Max. The next numbers 2 and 1 indicate that the sleeve is aluminum and the stem is steel. The next 2 means that it's a flush head rivet. The -4 means that the rivet diameter is 4/32 or 1/8 of an inch. The -2 means that the max grip length is 2/16 or 1/8 of an inch, which I believe is the lowest grip length that they sell. They certainly have longer grip lengths, but not shorter ones. Then the strength is very good, at least according to Cherry. The shear strength is 664 pounds and the tensile strength is 285 pounds. Very strong rivets. So the downside is the cost. They're about 70 cents a piece. So if you were to buy 10,000 of them to replace your solid rivets, that'd be about $7,000. Now you can probably get a quantity discount, but it'd be somewhere in that ballpark. It's not quite that bad because for solid rivets, they require a lot more tools. They require a $600 squeezer, a $200 rivet gun, bucking bars at $200 a piece, things like that. So, but still, using Cherry Max rivets would be pretty darn expensive. So the question is, you know, is there a cheaper rivet that maybe you could use? So I looked at some of the other Cherry rivets. Their cheap ones are the Type N rivets. And the one that I have here is the BSC-43. And the B means it's an aluminum rivet, with the S means it has a steel mandrel, which doesn't matter because that gets thrown away anyway. The C means that it's a flush head rivet. The 4 means that its diameter is 4/32 or 1/8 of an inch. And they do have 3/32 Type N rivets. But I picked the Type 4 because the Cherry Max was a Type 4. And I don't think they have 3/32 Cherry Max rivets. Then the last 3 means that the maximum grip length is 3/32 of an inch. And according to Cherry, the shear strength of these rivets is 200 pounds and the tensile strength is 325 pounds, which seems like it should be just fine. Particularly with the thin metal. Now, you know, when you're riveting thicker metal like the spars and things like that, maybe, you know, a number 4 solid rivet would still be better. But these are still pretty strong. And these are only 16 cents a piece. So, you know, you could easily build an airplane, you know, it would be a little more, well, like I said, the cost of the tools for the solid rivets would probably make up for the additional cost of the rivets, for the pulled rivets. But the advantage would be, of the pulled rivets, would be the build time. You could probably save yourself 500 hours of build time by using pulled rivets instead of solid rivets. And there are planes that use pulled rivets. I believe the RV12 uses all pulled rivets. And the Sling TSI uses all pulled rivets. Unfortunately, I don't know what specific rivet they use. If anybody knows, please leave a comment. I'd be curious to know exactly what rivet Sling is using. Let's see, another disadvantage of the pulled rivets is, in particular for these cheap ones, is they all have a hole. They leave a hole in the center of the rivet. And so when you go to paint your plane, you would probably want to come back and fill them with epoxy or something like that, make them look a little nicer. So anyway, it's kind of interesting. It seems to me like it would, you know, be a viable option. You know, maybe Vans should consider having an RV10 Model B that is pulled rivets. Okay, that's it for this video. If you want to recommend these videos to other people, the thing to do is to subscribe, give them a thumbs up, or leave a comment, and that will tell the YouTube algorithm to recommend these videos to people with similar interests. And as always, I'll put any links in the description. In particular, I'll put links to my previous videos on rivets in the description. And I'll also try and include a link or two about the Cherry rivets and the Cherry Max rivets in the description. So that's it. Thanks for watching.